distributed SQL streaming database, and it's open source, but we definitely have the cloud version, and it's under open source on the Apache 2.0 license. So RisingWave is probably one of the fastest growing stream partition system in the world. And you can check out GitHub and check out the Slack community channels. So RisingWave is has already been adopted in a lot of, I think probably hundreds or even thousands of companies. Some of the verticals we are focused on includes like fintech, including the financial services, like banks, right? And trading firms, securities, and the other one is gaming, right? Well, and online gaming, entertainment, multimedia, and also the new energy, right? There are a lot of companies building new stuff on the energy domain, and also manufacturing. And definitely we also focus on pay special attention to the Web 2 technology, basically internet, all kinds of the SaaS services, right? Oh, all right. And so we started the company and the project 3 years ago, and actually 3.5 years ago. So the project has already been pretty solid. But today I'll be talking about RisingWave, and definitely we experienced a lot of things where we covered a lot of challenges over the last 3 years. But I will only use 30 minutes to explain, okay, what we've done and what's the main challenge we have, and with the main technology what's the main technology behind the scene. Okay, so let's go back to 2020 when I was doing Redshift. So if you're not familiar with Redshift, probably and if you're, let's say, Google customer, then probably you're more familiar with Google BigQuery, right? Or you're definitely may have heard the name of Snowflake, right? Basically, Redshift, BigQuery, and Google and the Snowflake data warehouses. So these systems are pretty, they're definitely great technology, and they are very good at processing batch data. So for Redshift, most of the customers did was that they will have the data stored in S3 or stored in some other places, or batch data stored in S3, right? And then they batch load the data from their object store to the data warehouse. And then if you want to generate a dashboard, or let's say you want to show some results, right? Then we will just type in some SQL queries and then show what's going on in the data, right? To gain some insights from the data. That's what Redshift does. That's how Redshift users use the system. So yeah. So let's say that so some people will say that how do we use Redshift to generate, let's say, refresh results, right? So refresh our refresher results so that we can gain real-time insights, right? Or to gain some latest insights from the data, right? What people usually do is that they will actually use some orchestration tools like Apache Airflow, right? And so that's where they will create frequently, actually periodically process execute the same SQL query. And then this dashboard will be refreshed every 6 hours. But over the last few years, the trend we found is that a lot of people are moving from batch to streaming. Actually, I don't know what's the exact percentage, but 45, 50, or even 60% of people are actually trying to connect the data, send the data from Kafka or in Redshift or in AWS is actually Kinesis, right? And from Kafka or some other messaging queues to Redshift and to their data warehouse, and then generate the results. So how do we do that? Well, definitely we can still, we can definitely directly connect the Kafka and with Redshift, and then still do batch processing, right? But the problem here is that a lot of people really want to gain real-time insights from the real-time data, right? Because the streaming data from Kafka is real-time. We really want to see some fresh results from and gain some real-time insights from my streaming data. Then can we just still use Redshift? The answer is probably no. Why? Because Redshift is not that efficient in processing real-time data, because it always does the batch processing, which means that it always have to scan the entire table. It could be terabytes of data, right, or even petabytes of data. It could be super slow. So Redshift is definitely not the right answer. So then, how can we process the data from Kafka, right? Well, how can we process the streaming data and gain real-time insights? Then definitely we definitely want to use a system that is optimized for stream processing, right? Because in Kafka it's streaming data, and we really want to process the streaming data, right? We really need to have stream processing capability. And we want to use a system that is super easy to use, right? Well, because nobody really wants to spend a lot of energy in maintaining or operating the system, right? And definitely we also want to make sure that the system is trustworthy, right? So how do we do that? Can we just rely on some existing systems? Well, one system definitely, I definitely tried out different systems, and the one system the first system came out in my mind is Redshift materialized view. I mean, the component, right? Redshift materialized view. Redshift materialized view, what is materialized view? Materialized view is basically a data storage, basically a data structure that maintains results of a query, right? In Redshift, if you want to create a materialized view, the only thing you need to do is actually just type in this statement, right? Create a materialized view, let's say my MV as your statement. So that will periodically Redshift will execute these queries, and so that we can see the fresh results in this materialized views. Well, is it the right solution for Kafka users? Well, unfortunately, probably not. Why? Because Redshift materialized view is still doing the batch processing, and the behind the scene, what it does is that it will actually track or periodically to track. Okay, what's the data set we have? What's a new data set that is inserted into the database, right? Or data warehouse, and then it will do the computation on this data set, and then apply the results to the previous one, so as to refresh the materialized view. Well, this technology is not, this mechanism is definitely not streaming at all, and you cannot, it can be super slow if the data set becomes big. And another problem here is that, this can cause the huge performance interference to other queries, concurrent queries. So Redshift is probably not the right answer for us. And what about some other systems? Some people may come up with a name, right, for ClickHouse. ClickHouse is one of the world's probably fastest database systems, fastest OLAP databases, right? It's definitely, in many cases, it's probably faster than Redshift. And in ClickHouse, there's also a concept called materialized views. So people may think that, can we just use ClickHouse materialized view to do the real-time analytics, right, to refresh the results frequently, right? Well, unfortunately, it's great. Well, you definitely, for some queries, you can do that. But, there are definitely a lot of limitations. One thing here is that it only does the asynchronous refresh, meaning that you have no idea about when the materialized views will be refreshed. And the second thing here that if you are familiar with Kafka or KCDB or some other technologies, you will know that there are a lot of streaming specific function operators like time window functions, like watermark, and hopping window, all these kind of things. ClickHouse don't really have that, which means that if you want to do this kind of thing, then probably ClickHouse is the right answer. And actually, the third thing ClickHouse missing is that it actually does not really have the right fault tolerance model. Think about in stream processing, we always do continuous stream processing, right? But what if the system gets crashed, right? If the system gets crashed, we really want to recover the system at once, right? But ClickHouse lacks the capability of better managing the state to recover from failures. So because of these reasons, ClickHouse is probably not the right answer. Then what about the next one, Flink? Yeah, definitely there are a lot of great technologies like Flink, Apache Spark, and Spark Streaming, KCDB, and the Flink is definitely one of the best solutions in this market, right? Can we just use Flink to do the stream processing? Yeah, definitely, sure, you can use that. And it's fully fledged stream processing capability. But I'm a database guy, and when I used to Flink, well, actually, I was part of I was actually a contributor of Flink actually 10 years ago, which actually 11 years ago in I think it's 13 or 14. I was a contributor of Flink, and I actually drafted the first version of the stream processing engine of inside of Flink. You can check out my code. So Flink is definitely great, but the problem here that it has two limitations. One is that it has drastically different user experience. If you are Postgres users or if you are Redshift users, you will find that okay, Flink SQL is definitely another world, and not to mention the Flink Java or Scala or some other language, the wrappers, right? It's definitely totally different user experience. So we have to spend a long time to learn the system, right? And definitely that's definitely limit our productivity, right? And there are some other drawbacks of Flink, and I will discuss later. So after evaluating all these kind of systems, we believe that definitely there will be some chance for us to build something new, and so as to bring a better system for the users to do the stream processing, to develop a stream processing application. And that's why we developed a system called RisingWave. The design principle of RisingWave is quite simple. It only focuses two things. One is ease of use, simple to use. And the second thing is trustworthy. What trustworthy means, I will explain later. So for ease of use, well, there are actually two things. Well, one is that how people can interact with the system. And the second question is that how we can build complex applications using the system, right? Because if we want to build a simple application, we can just write any Python code or Java code or any SQL, use any system. We can definitely build simple applications. But the challenge here is that how can we build a complex application? So to answer this question, our answer to this question is that we want to make sure that the system is Postgres compatible. So don't get me wrong, I believe that definitely MySQL and some other Oracle great technologies. But I believe that probably in the future, Postgres SQL is probably the only legit SQL in the world. So we definitely bet big on the Postgres SQL, and we believe that the system should have bring user with the Postgres style experience. So RisingWave actually speaks the Postgres SQL is totally wide compatible with Postgres. So which means that as long as you know how to use Postgres, you essentially know how to use RisingWave. In Postgres, definitely then how do we use RisingWave to build a stream processing application? Well, in Postgres, there's a concept called matrice view, right? In Postgres, you actually have to refresh the matrice manually. But in RisingWave, we offer exactly the same user experience. That is, you can just create a matrice view. But after you create a matrice view, it essentially becomes a streaming job, which means that it will continuously refresh the matrice views every time a new event comes in. So let's say that if we get a new event comes in, then the behind the scene there's a streaming processing engine that will continuously consume the streaming data and then refresh the result, right? And then show the result in your matrice views. That's how RisingWave works. So definitely as I just mentioned, because we are Postgres well compatible, which means this means that as long as you if we want to use some, systems that are compatible with Postgres, like dbt, dbeaver, or even VS Code, right? Well, VS Code actually have the Postgres plugin. You can just use it with RisingWave. That's super cool. And then the next question is that how can we build a complex streaming application, right? So if we want to just build a simple application using, any streaming engine, then let's say that's what we want to use Flink, right? It's just one single application or one single streaming job, then it's super easy, right? So you can use Java, you can use SQL, you can use some other Python languages, right? But the challenge here is that what if we want to build a long pipeline right? Then we have to introduce another system called Kafka, right? Because why we need to introduce Kafka? Because Flink doesn't really have the storage, right? So you actually it consumes data and emit the results and deliver to some downstreaming systems. If we want to connect two streaming jobs, let's say two Flink streaming jobs, then essentially we actually have to have Kafka sit in the middle, so as to basically buffer the intermediate results, right? And also there are another system we actually have in addition to Kafka, we actually have to bring another system, a database. Why? Because Flink doesn't really have Flink doesn't really have the storage. If we really want to check the result in a database, or let's say we want to just use SQL to check the result, essentially you actually have to bring a new database into the data stack, right? So you can imagine that how complicated it will be if we want to use conventional stream processing systems, like no matter whether it's Flink or whether it's like the Spark streaming, right, or even SAMS or some other systems. You actually have to maintain all this kind of very complicated data stack, right? But in RisingWave, the only thing you need to do is to create a materialized view. And the magic here is that RisingWave allows you to create a materialized view on top of another materialized views, which means that as long as you, all these materialized views are consistent and will be refreshed upon data arrival. So that's about the user experience, right? And then, okay, so that's just one single part of the story. The second part I want to talk about is trustworthy, right? So what does trustworthy mean? Well, whenever we talk about a system, whether a system is trustworthy, we do not really, we actually talk about several things, well, at least three pieces, well, three aspects. One is performance, right? Well, because we don't really want to have a super slow performance, a system that is will get stuck when processing streaming data, right? And we also want to make sure that the system is reliable, right? Reliable means that if once node occurs, any node occurs, it can be recovered from the failure instantly. And the third aspect is essentially elastic. Why elastic is important? Because as you can imagine, for streaming processing, the streaming workload can change. In the daytime, if you build some applications, you will know that in the daytime we probably have a lot of traffic, but at midnight probably no use the app, right? So workload can fluctuate. We really want to make sure that the system is can be elastic, so that we can provision necessary results for the system instead of just provision the peak results to the peak usage, right? So then how do we achieve this? Well, all these kind of three aspects. We use a technology called the mechanism called S3 as the primary storage. I know that for S3 as a primary storage, probably not everyone is familiar with the term, right? What is S3 as a primary storage, right? But you probably are familiar with some other terms like decoupled computer and storage, right? Shared storage architecture or tier storage, right? And if you are not familiar with all these kind of things, then the only thing you need to remember is that just like Snowflake-like architecture. Snowflake-like architecture means a lot, right? It means that essentially you put out storage in the S3, right? In the remote storage, and you only need to take care of your computation layer, right? And the computation layer and the storage layer can scale infinitely and independently, right? And this is so-called Snowflake architecture. The Snowflake architecture brings a lot of advantages, right? And the first one is essentially performance. In stream processing, the most challenging part is not about how we process the data, but how we manage the internal states. What is state? So let's say imagine that we want to join two data streams, right? Two data streams. One is impression stream, and another one is click stream. This is if you want to join these two streams, then it's essentially an ad monetization application, right? If we join these two streams, then we essentially will know which impression leads to which click, so that we can charge the ad publisher, right? And So yeah, if we want to do this join, then we actually need to maintain a state. What is state? In this query, the state is a state for the join, and which essentially the hash table for the one. Actually, there are two hash tables we need to build for this join. One is the hash table for the impression stream, and another one is hash table for the click stream. If once we have this, these two states must be reliable, which means that if the system crashes, then we always need to recover the state, right? So that we can continue the processing. The challenge in stream processing is that how we can manage these states, right? In all the world, no matter whether it's Spark Streaming, Flink, or KZDB, or like Samza or some other systems, all of them adopt a technology called for the coupled compute and storage architecture. If you're not familiar with this term, just remember that it's basically like a Hadoop-like architecture, right? So what it means that if we want to scale let's say the cluster from one node to three nodes, what we do is that we will essentially partition the state into three pieces and put every single piece into one single machine. And for that single machine, it only need to the computation, the CPU in that machine only need to access the data, or access the partition, access the shard or data shard, right? Placed in that node. That's a so-called coupled computer and storage architecture. This architecture is super efficient, which means that because the CPU only need to access the local data, right? It can be super efficient. But the problem here is that in stream processing, the workloads can fluctuate, which means that the state can grow, right? If the states can grow, then it can hit the limit of the storage, right? Well, the storage size, right? Once if we hit the storage size, well, let's say if the state size is larger than the state size, what will happen? Probably the system will crash, right? That's a problem. That's essentially the problem of most of the existing stream processing systems, right? But RisingWave actually adopted another architecture, as I just mentioned. It's the so-called coupled computer and storage architecture. In this architecture, we directly put a state into the remote storage, which is S3. And if we want to scale from one node into three different nodes, the only thing we do not need to do anything to the state. The only thing we need to do is that we only need to create the three different machines and ask these three machines to access the data stored in S3. That's it. Right. So in this kind of in using this architecture, we no longer need to worry about the state size, right? Because S3's volume is kind of like unlimited, right? We never need to worry about we will use up all your S3 quota, right? All S3 capacity, right? So this makes things much easier, the entire architecture much easier to deal with, right? So with this architecture, you can imagine that whenever we handle the complex queries like multi-way joins, 10-way joins, 20-way joins, or even 100-way joins, we no longer need to worry about whether the state will be too large because the state is put in S3. So yeah, that's the advantage of the S3. That's one of the advantages of the S3 as a primary storage, right? But now let's take a look at one problem that is a failure recovery, right? As a distributed system, whenever we execute a distributed system, we want to make sure that the system can be recovered from failure instantly, right? Okay, then how do the conventional stream processing systems deal with failure recovery? Let's say that one of the single nodes failed, right? Then in Flink or in Spark Streaming, what they will do is that they will essentially create a new machine and ask all these three machines to load the checkpoint from the persistent storage. Could be in old days it's HDFS, but in modern days it's S3, right? Load the checkpoint from the persistent storage, and then replay part of the logs, right? That's what they do, right? But this thing looks pretty simple. But the problem here is that recovery from checkpoint can take minutes or even hours. Right? It totally depends on the checkpoint size. Let's say that if your state size is, let's say, 1 terabyte, right? Reloading the data from reloading a checkpoint from the S3 can take hours. You can just do the math, right? Well, you can just calculate for the network, the bandwidth and calculate how long it will take. It can easily be increased to hours. But for RisingWave, well, I mean, what will happen if a single node failed in RisingWave instance? Well, RisingWave's recovery mechanism is quite simple. That is, the only thing you need to do is that we just create another machine and ask that machine to read the data from remote storage. That's it, and the recovery will be done in seconds. So that's it. Well, there's no downtime. So actually last month I was in Singapore and I was visiting one of the biggest technology company in Singapore, and they told me that they were using Flink, and the system at midnight the system crashed, the Flink crashed, but unfortunately the DevOps their SRE failed to reload the checkpoint from S3. So which causes the system to be down for hours. But in RisingWave, the thing will be totally different. That is, if the system crashes, then you can just put another machine and the system will keep running. That's it. Okay, then let's talk about elastic scaling, right? Well, just imagine a case that we want to scale because of workload spikes, right? Well, we want to scale one of the nodes from scale the system from, let's say, 1 node into 3 different nodes, right? So what we can do? What we can do? In the old days, what we do is that we have to create 3 nodes and then ask the system, no matter whether it's Spark Streaming or Flink, to do the so-called state migration, to migrate state from 1 machine to 3 different machines. And the system will suffer from downtime, and the system cannot keep running until the state migration completes. So we will have to suffer from minutes or hours of system downtime. But in RisingWave, elastic scaling is as simple as failure recovery. What we do is that we can just create 3 different machines, and then it's done, and it's done in seconds. So that's how RisingWave works for elastic scaling. Actually, we just talk about the failure recovery and the elastic scaling, but actually one simple very interesting use case in stream processing, not use case. Well, one very interesting challenge in stream processing is that what we can do when schema changed, right? Let's say we have an upstream system which is MySQL, Postgres, or MongoDB, right? For the MongoDB semi-structured, but let's say it's MySQL or Postgres, right? What will happen if their schema changed, right? Then conventionally, the stream processing system, what the stream processing system will do was that they actually have to, drop the entire state and then recompute from scratch, right? And the recompilation can take hours because you can just imagine that, how much data you stored in MySQL Postgres, right? You actually have to reload the entire state from reload the entire data from your optional database, and then do the computation, do all these computations to recover the state, right? But in RisingWave, because of this architecture, one very interesting thing here is that we can actually do so-called serverless schema change. What the mechanism here is that essentially during the recovery time, we can essentially add more nodes into the RisingWave instance. So that let's say that in this case, we can actually use 6 different nodes to reload the data from your optional database. And after finishing this computation, then we can just go back and scale down into two nodes, right? and the schema change can be done within, let's say, seconds or minutes. You can just do the math, right? Let's say that if you use, let's say, Flink or Spark Streaming, and let's say it takes 1 hour, right? But in RisingWave, you can just use, let's say, 10 times resources, and then you can just drop the recovery time from 1 hour to 6 minutes. Right? All right. Then the next so we have already discussed how the internal architecture of RisingWave, and we also discussed how we deal with the state management, how we do the failure recovery, how we do the elastic scaling, and how we do a schema change, right? The next question I have to answer is that what's the relation between RisingWave and Flink? Is it a pure replacement, or is it like we actually hate each other, right? Well, definitely. I mean, I think the answer is that you can decide whether what's the relation between RisingWave and Flink. Why? So I can just simply ask you this question: what's the relation between Spark and Snowflake, right? Okay, I know that Databricks has a very tricky relationship with Snowflake, right? But imagine what if it's just a Spark, right? What's the relation between Spark and Snowflake, right? So in many companies, it's actually just coexist. Why? Because in many applications, you actually have to use Spark's Java layer or Python, right? PySpark to process some batch data, but use Snowflake to run SQL, right? Forget about the Databricks offering, right? Similarly, in the stream processing domain, we actually have the similar case, right? For Flink, people can still use Flink's Java offering. Actually, I know that many people just use Flink as a Java framework, right, to build a streaming application. You can keep doing that, but RisingWave is specifically designed for the database, users and the artifact. It makes a lot of sense for database users to use a Postgres compatible system, right? And there are a lot of RisingWave and Flink shares a lot of similar capabilities, like executive ones. We both support executive ones. We both support watermark. We both support time wandering functions. But for Flink, it has the Java API and Python API. In RisingWave, what we offer is all kinds of the database capabilities, like functionalities like database systems, query serving, Postgres ecosystem, Python, Java, UDF, transaction semantics, and many others. So I think for Spark and Spark Streaming and Flink's best page will be that they are actually great systems, and they actually provide extensive stream processing capabilities, right? You can use SQL, you can use, probably you can go down to the table API or go down to the data streaming or data set API to leverage their Python API and the Java API, right? But for RisingWave, the RisingWave page will be that we try to help people to simplify the stream processing experience. You do not need to manage a lot of very complicated data stack. You can just use one single database system to process or to build your complex stream processing application. And definitely, it offers pretty advanced system maintenance capabilities like high availability, dynamic scaling, high performance in streaming joins, speedy schema change, and many others. All right, and definitely there are some other database features like object encryption and many others, right? So yeah, let me just spend 3 minutes to do a pretty quick demo. So how to create the hold a sec. Do you know how to create? Do you know how to quit the screen sharing?
Are you using that for your
I can just
escape?
Yeah. Okay, I see. Yeah. Yeah, you can see this one, right?
Yeah.
And in this demo, I will not do a demo on my own. Well, I'll ask the AI to do a demo. Okay. So what do you want to do? What kind of application you want to build? Let's say that how how to consume data from Postgres consume and Kafka. Join these two streams and send results into Snowflake. Okay, Snowflake. I don't know. Let's try. Let's try. Roasting. Boiling water. Okay. Okay. You actually need to do three things. Okay. Keeps. Yeah. Yeah. It generates a lot of results, right? It's a pretty good, nice demo, right? Okay. So yeah, so it's not ChatGPT, okay? It's not like it's actually a bot built up by a startup and called Run IRM, right? So basically, what it will do is actually it will ask you to so you only need to follow these three steps. The first one is actually you can create a source, right? Define the sources for Postgres and Kafka. And then the second thing here that will create a materialized view. And the third thing is to create a sink. So to create a source, the only thing you need to do is that to write the SQL query, like create a source. Let me try to enlarge it. To create a source, right? And put some parameters here. And then for Kafka, similarly, you can do this one. And then create a materialized view to a join. Okay. The materialized view's name is view Kafka join Postgres. Okay, nice name. And then create a sink, right? And then for this one, it will create a materialized view. Basically, it will boost put a streaming job, right? And for this statement, what we do is that it will deliver the result from view Kafka join Postgres, right? This is a materialized view's name, right? But I don't really like this name. It's too long, right? And then after running this query, it will send the data into Snowflake. It's not correct. It actually supports Snowflake. Okay, that's a bug of the. It's not a bug of RisingWave. It's actually a bug of the bot. But anyways, yeah. So yeah, you can see that's okay, how easy it is to build an application, right? Using RisingWave, right? Yeah, don't trust the bot. Yeah. Anyways, yeah, that's my talk. Yeah, thanks.
Questions?
Yeah.
Go ahead.
Can you talk more about your UDF support?
UDF support.
Yeah, we lost it that. I found it interesting.
Ask AI. So yeah, let's try it. Yeah, let's try it. Yeah, is it? So basically, we support different UDFs. We support Python UDF, Java UDF, C++ UDF, Rust UDF, JavaScript UDF. Do you know why we support JavaScript UDF? Because the Crypt guys really basically write a lot of applications using JavaScript. So in RisingWave, we support the user experience. I mean, from the user experience perspective, it's quite similar to Postgres. It's essentially the same as the Redshift. And then people may ask, okay, what's the difference between RisingWave's UDF and Flink's UDF? So in RisingWave, you can actually scale in and out the UDF service, the UDF server, but in Flink also in some other systems, it actually belongs to the job, streaming job, and you cannot scale it independently. Yeah.
How do you monitor whatever is happening?
Monitor what?
How do you monitor the data flow?
Okay, so basically we have pretty fancy observability toolings, and so in RisingWave we actually we have a concept called epoch, and the epoch actually tracks the progress, and essentially you can you can ask AI, but essentially the idea here is that we can use the epoch to track the progress of every single material view, and then you will know whether there's some still whether you always see the fresh result or the result is still
How does it fit into the Streamhouse architecture with Apache Pymon and where the industry is going?
RisingWave has a pretty good support for Iceberg. It's not because some other companies acquired Iceberg, but it's mainly because we definitely as we all know, Iceberg is quite popular, right? And we actually donated a project called Rust Iceberg. You can search a project, and it's actually under Apache Foundation. And we actually use that because basically, if you use let's say if you use any Rust system, you can actually dump data, interact with Iceberg using that API. So our answer, we definitely believe that streaming warehouse or streaming lakehouse is definitely a future. And what people usually do is that they will use RisingWave to consume data from operational database or Kafka or some other systems, and then do streaming joins or basically manipulation, stream processing, and then dump data into Iceberg format. So and then essentially you can use some other systems like ClickHouse, like Trino, and some others, right, to analyze the lake data. So and then essentially RisingWave can also do that, but totally depends on the preference because we know that in many companies where they just use one single system that is Trino to do the federated query, right? So we allow people to do that. And DuckDB is really great, to be honest.
And can you talk about using the Iceberg from RisingWave itself? Can you query the Iceberg data?
You can,
So is it more like a streaming database or analytics database in this case?
That's a pretty good question. RisingWave is a streaming database, and we use row store. So basically row format.
Mm-hmm.
We do not really do the column format. But in the future, probably we will do that. But at the moment, we still use the row format. Why we do that? Because for streaming, for several reasons. For streaming applications, typically people do you can imagine RisingWave is you can imagine that Snowflake is the data system for historical data, but RisingWave is essentially a system for regional data or real-time data, right? 7 days data, 1 day data, or even 1 hour data. Think about trading firms, for them it's just 1 day data, and for some other companies, probably 7 days data. So for this kind of short-term data, 7 days is probably not big, right? But for this short-term data, you don't need to have a fancy column store. Row store is fast enough because we can do parallelism. And modern CPUs are super powerful, and we also support SIMD instructions. So basically, you can use vectorization. We actually support vectorized scan, and to accelerate the query processing. So it's more like, to answer your question, it's more like a streaming database.
But if I make a query against the
Iceberg, then it will be loaded from the Iceberg and then do the computation. So
do you copy all the data to RisingWave format?
That's yes. I can tell you why. Because for any system, you actually have to do that. So I can tell you why. Because for streaming, because for Iceberg doesn't really have the CPC. Yeah. So that's a problem. So some people will ask us about how I can join, let's say, a streaming event stream from Kafka with, let's say, my Iceberg table, right? Our recommendation is always that you unfortunately have to load the entire table from Iceberg to RisingWave. And there's no workaround, to be honest. Why? first thing here that it doesn't really support CPC. And second thing here that okay, if you do not really load the data from Iceberg into RisingWave or into any other systems, then accessing data in Iceberg could be super slow. Think about it, it's essentially Parquet, right? Well, a batch of Parquet files. It could be super slow, and it doesn't really fit into the streaming application, right? Well, streaming purpose.
If I'm building a streaming application, I have lots of nodes in my topology. So my data flowing through it, and you depicted it. So Flink here, or Kafka, right? So that data flow, if something goes wrong with it, I can go look at the data in Kafka and I can see what's going on, right? I can go and use any Kafka tool to go back and forth in time, see what's happened to the data, and then I can evolve my streaming architecture quite easily because it's going through Kafka, right? That's what everyone here probably understands is, whether you're using Flink or Kafka streams, you're saying that you do this, instead of going through Kafka, you use prefixed S3 buckets to give you scaling, because S3 buckets will give you like 5,500 GET requests a second. So that's your scaling model. So for each of your prefixes. So then if you're doing node that's outputting to a series of prefixed S3 buckets to keep scaling, and then you have this hierarchy of nodes and you're going through S3 prefix buckets, then what is the process of actually going and debugging what's going on to see why your topology isn't working? With Kafka, I can go and use any Kafka tool to go back and forth and have a look at it. What would it be like with what you're defining here?
Okay, so the answer here that's so there are two parts. Well, one is that's how RisingWave fetches data from Iceberg. From S3. And the second thing here that how do we monitor the application, right? Well, essentially these
how
are
do I debug it if something's gone wrong? What is the process?
Okay, so first of all, we do not really expose the underlying state to the users. We do not really expose unless you want to hack, for sure you can do that. But by default we do not really expose. But we provide people a tooling, basically a set of toolings to monitor the progress. Essentially, as I just answered, so we actually have a concept called epoch, and you can just query like a simple select query, and to query for every single material SU, what's the progress look like, right? Again, how many tuples it have already processed, right? Probably the first one is 1,000 and second one is 990, right? And you can easily visualize in the Postgres table. That's number one. And regarding debugging, unfortunately, we do not really expose that or point the details to the user because we think that the user should focus on applications instead of we focus on the debugging. As a system builder, we actually focus on make sure that's where the system is correct. And for the accessing S3, in many cases, we do not really need to access S3 because we actually have the caching layer. Just to think about it, so for Snowflake, it doesn't really always access S3.
But if you bring up a new node, you do need to access.
Yeah, that's right. Yeah, if you want to, yeah, that's right. Yeah. So okay,
But if all your data is on S3, it's going to get to cache. So cache doesn't
really exist, right? And
sees it.
so yeah, for the first, so let's say that if you want to do let's say failure recovery, right? Or if you want to do elastic scaling, so that you want to bring some new nodes, right? In this case, typically yes. Well, for the first few seconds, minutes, you will feel that the materials or the streaming jobs will is not the materials isn't fresh enough. The result isn't fresh enough, and that's because there are some cache miss, and you have to frequently fetch the data from S3. Right, that's a problem. So yeah, so you will see
Kafka streams and Flink all have to do that as well, whether they've got a local RocksDB or they're doing CDC through it.
Oh, that's okay.
I mean, they're not going through, but Flink's more flexible too. So
Yeah, flexibility wise, yes. But regarding the availability wise, availability, RisingWave is highly available, which means that, okay, I mean, if the system crashes, you will not be stalled. You can still process. Yeah, that's the difference.
So you show that the Flink is writing snapshots to S3 and then recovering from the snapshot. What's the difference? What kind of increments you writing to S3?
So we write the directly write the state into S3.
Every little change?
No, not every little change. We'll definitely buffer. We do the buffering. And
so what's the durability? So obviously you're writing every stuff into S3. What happens to the data before it's written to S3? Do you replicate between the nodes?
okay, that's a pretty good question. Yes, we actually essentially for the small changes, let's say, so we have a concept called epoch. For in detail, by default the epoch is, if I remember correctly, it's 100 millisecond or 200 millisecond. So if so basically, for every single 100 milliseconds, we will actually push the data into S3. So that will, if let's say system crashes, right? The only data you potentially could lose is within this 100 millisecond. So the problem here is that how we can recover this 100 millisecond data, right? You fetch the data from S3. Oh, not
From
S3,
the
from upstream. Upstream. Yeah.
That makes sense.
What about processing failures? So I've got halfway through something. How deterministic is the failure and recovery states? So with Kafka, if I haven't processed something, the offset hasn't been committed. So I can have stream processes run out of memory, and I know that it's just going to be restarted, another one's going to take over, and it's going to carry on processing because the offset wasn't committed, so it's just going to carry on, regardless of it being a bit lumpy. So I do have those guarantees, and I can set exactly once, those kinds of things, but I know that works because Kafka's providing me with those guarantees.
Yeah, we also provide exactly one's guarantees, and actually that's the default guarantee. We actually the mechanism is that we actually have the metadata service, and the metadata service will actually persist. The metadata service is we allow people to bring your own metadata service. Could be Postgres, could be any system, as long as you trust, right? Postgres. Let's say that's what it's Postgres. We essentially persist the progress, which is epoch ID in the metadata service, so that you will always know that how much data you ever, how much amount of data you ever processed.
Do you have a concept of offsets? Or is it always epochs that you're talking about?
Offsetting.
Kafka has an offset, it's like a
record. We keep track of it. Yes. Yeah, we keep track of Kafka's. If it's Kafka, if it's upstream.
No, but when you've got your hierarchy or your data flow of processor, they're all going through S3 buckets, right? Are you tracking the processing of each one of those?
Okay.
Similar to offset, so if there is a failure, you know where things are.
So let me clarify a little bit. So we actually track the epoch for every single materialized view. So basically, the materialized view, for the first materialized view, you can.
But epoch's time, I'm talking about offsets because time is not really relevant. It's just like where am I?
I know. Yeah, I know what you mean. Yes, we do that. Yes, we do that. Yeah.
Is the epoch you're referring to is like a block time in a blockchain? Is it equivalent to that?
I'm not an expert in blockchain, but we do support a lot of crypto. We actually support one of the world's largest crypto exchange. But actually, so back to your question. So you can imagine that the epoch is essentially a wall clock, while the offset is the, let's say, number of cycles. That's a different concept. Yeah.
Could you tell us about some of the large deployments?
Yeah, I just mentioned. Okay, so I'm not sure whether it's recorded, right? Yeah, it's recorded. It's recorded, right? It's recorded. Okay, so we can talk offline, but I can give you some of our customers. One is as you just mentioned, it's essentially the world's top 2 crypto exchange. And the other one is the world's essentially the largest capital management company. And also in Europe, publicly Henkel is our customer, and we are signing. I think we're in this room. Yeah, if you